Welcome back, guys. This is the fourth video about vectors, and we are talking about generalizing the ideas to beyond 2 dimensions, up to 3 dimensions, and even as many as n dimensions. Now, before we get started on that, I just want to give you some motivation for it. A lot of people say, why go beyond 3-dimensional space, or even 4-dimensional? They'll be comfortable with space-time, but anything beyond 4 dimensions bothers them. Actually, we can have as many dimensions as we want. Every dimension represents what we're thinking of as an independent variable, a variable that's not really affected by the other variables. Like the x direction and the y direction, those are completely independent of each other. And that has something to do with perpendicular vectors. We're not going to get into that here. But just know that there are lots of things that go beyond 3 or 4 dimensions. Just for example, the temperature in this room. I'm sure there are lots of factors that affect the temperature. I could say the temperature in this room is affected by, the thermostat setting and how much, what is it called in the walls? I'm losing the word right now, but how much insulation I have in my house. It could also just very simply depend on temperature T could depend on X, Y, and Z, so 3 spatial coordinates. And it could also depend on time. And that's giving us this, so we've got 4 variables here, and for each of those 4 variables, I'm getting a 5th variable, temperature. I want to use capital T again, but I've used it to name my function, so I'm going to use the letter W to represent temperature. If I wanted to graph this, the domain would be a subset of 4-dimensional space, and the range is a real number. So if I want to graph it, I have to be in 5-dimensional space. Can't really do that because we can't see beyond 3 dimensions. And so there is a very good reason that we talk about n-dimensional space. There are also lots of problems in engineering and the sciences where you've got 15 independent variables. You might be optimizing some function that depends on those using matrices and a lot of the math that we talk about in linear algebra. So n-dimensional space is really important, but I just wanted to show you how everything that we've talked about so far goes from beyond 2D to 3D and as many as ND. So component form. In 2D, let's say we've got a vector u. It can be represented by components u1 and u2. You can imagine how that extends to 3D. Here I had an x component and a y component. If I go to 3D, now I'm going to have an x component, a y component, and a z component. When I go to ND, I can't really call it x, y, and z anymore, but I'm going to have one component for every dimension. So I'll have a first component, and a second component, and a third component, and a fourth component, all the way up to an nth component. And this is fine. The mathematics is going to work nicely here, just like it works nicely here. We also talked about the vector from P to Q. From P to Q. In 2D, my vector, or my point P might be x1, y1, and my point Q might be x2, y2. Then the vector PQ, as we've seen, comes from taking terminal minus initial. We do x2 minus x1 and y2 minus y1. That's 2D. In 3D, instead of points having an x, y, and a z, instead of points having an x and y, my points are going to have an x, a y, and a z. So P might be represented by x1, y1, z1, and Q might be represented by x2, y2, z2. And you can imagine how we come up with PQ again. It's still terminal minus initial. We're going to do x2 minus x1, y2 minus y1, and z2 minus z1. Now for the next one, it's a little bit harder to stay consistent with my notation because I'm running out of letters, and I don't know which n letters I'm using. So in n dimensions, I'm going to use slightly different notation. Don't let it bother you. I'm going to call point P, P1, P2, all the way through P sub n. It has n components. And Q has coordinates. These are coordinates of P, not components of P. And Q has coordinates Q1, Q2, all the way through Qn. So the vector PQ starts at Q and ends, or starts at P and ends at Q. We still do terminal minus initial. It looks a little different, the subscripts, but the idea is the same. I'm taking the first one and I'm subtracting the first one. Terminal minus initial. And then I do terminal minus initial again. And then terminal minus initial again. And we keep going until we get n of them. Terminal minus initial again. And that's the vector PQ in n-dimensional space. Vector addition is the same. It's just exactly what you would expect. We add component by component. So if U has components U1 and U2, and V has components V1 and V2, in 2D, you've got U1 plus V1 and U2 plus V2. That's your new vector U plus V. In 3D, well, now my U and V have to have 3 components. U will have components U1, U2, and U3, because I'm in 3D. And V will have components V1, V2, and V3. And then U plus V will have 3 components too. Add the X components together. Add the Y components together. And finally, we add the Z components together. You see where this is going? If I'm in ND, my vectors have n components. So I go U1, U2, all the way up to U sub n. And I have V, V1, V2, all the way through V sub n. When I add them, I get U1 plus V1 and U2 plus V2 and U3 plus V3, and I keep going until I get U sub n plus V sub n. Totally fine. All the math works out just fine. Length or magnitude. This is fun. If V has 2 components, V1 and V2, the length of V just comes from taking those components, squaring them, and adding them, and taking the square root. Now we can prove that with the Pythagorean theorem, we could use it twice. That if I've got a vector in 3D, I just take the 3 components, I square them, and add them, and take the square root. Oops, square it, not cube it. In ND, do the same thing. You're just going to have n of them. Take the components, you square them, add them, and take the square root. That's it. That's 2D. That's 3D. That's ND. You can go backwards. What about 1D? What if our vector V had just 1 component? Is that the absolute value of V? I hope so. I know, this doesn't really make sense. You're like, it's a vector with a single component. It's a little weird. But you see the pattern. You've got 1 component. You square it and take the square root. 2 components. Square them and add them and take the square root. You've got 3 components. Square them and add them and take the square root. No matter what you do to find the length, you take the components, you square them and add them and take the square root. It doesn't matter how many dimensions you're in. So all the math generalizes very nicely. Nothing too scary. You can handle this, you can handle this. No big deal. I mean, it's a lot of arithmetic, but you can use a computer for that. That's what technology is for. Scalar multiplication. It's, of course, exactly the same. If U has n dimensions, C times U has n dimensions. Multiply all of the components of U by C. And U could be 2, so it'd be 2-dimensional. U could be 3, be 3-dimensional. It could be n equals 5. It could have 5 dimensions. That'd be fine. Scalar multiplication is the same. We also have standard unit vectors. Beyond 3 dimensions, the notation isn't as standard as we would hope. But in 2D, we've seen our unit vectors, I hat and j hat. That's our unit vector in the x direction. And our unit vector in the y direction, right? 3D, same thing. Got a unit vector in the x direction, but now my vector has 3 components. And then I have a unit vector in the y direction, but now my unit vectors have 3 components. And then I'm also going to have one in the z direction. It's 1 unit long and it points in the z direction, has 3 components. ND, usually I see it with these E's with a little hat on it to denote it's a unit vector, and sometimes you'll see some sub I, and this is for I equals 1 through n. So you're going to have E1, E2, E3, these are basis vectors, just mutually perpendicular unit vectors. And E sub I, that vector is just a bunch of zeros everywhere, until you get this 1. You're going to have 0, 1, 0, and then you're going to have a bunch more zeros at the end. It doesn't go on forever. There should be zeros at the end. That's it. This is a 1 in the ith position. That has a 1 in the first position. That has a 1 in the second position. That has a 1 in the third position. That has a 1 in the last position, or the nth position, the nth coordinate. Component, because we're talking about vectors. Everything holds. And it turns out all of these vectors in n-dimensional space are also perpendicular to each other in some sense. I think that's kind of cool. And talk to your linear algebra teacher about what sense, if you're really curious. All right. So that's where the similarities end, at least for this video. In the next video, we're going to talk about the coordinate system in 3 dimensions, and how these 3 standard unit vectors play out, and just getting ourselves comfortable with the 3-dimensional coordinate system that we use, which is right-handed. So stay tuned for that.